Okay, again, thank you all very much for coming, and I thank the organizers for this opportunity to present to you some recent bioanalytical methodology that we have been working on at Supelco in one of our R&D groups there in applied research. This is some developments that have come out over the last few years. And basically what I want to do here is go over highlight three particular areas that we have made some headway in ourselves. One was is looking at some alternatives for mobile phases, for reverse phase chromatography of peptides for LCMS. There's typical mobile phases that are done for that. At times can have some problems, some issues with peak shape, particularly if you're looking at basic pharmaceutical peptides. We'll follow that with some recent developments in a size exclusion chromatography, a product line that we have now, looking at some antibody fragment separations. And then shifting really into some small molecule bioanalysis is looking at some development of methods for reducing matrix interference with sample prep from plasma, as that is a significant problem. So looking at this first topic on LCMS separation of peptides, TFA is typically used for reverse phase separation of peptides with UV detection, and it's very effective for that, and that it forms an effective ion pair with basic moieties of peptides, and it controls pH well below that of the side chains of the carboxyl group so as to maximize retention of the peptides. TFA alone, however, is not suitable for reverse phase chromatography of peptides when mass spec is employed. Issues of the surface tension with these typical 0.1% TFA solutions precludes efficient nebulization in the source. And the TFA ions as well in the gas phase form strong ion pairs with the basic moieties of the peptides, again masking charge. So TFA, if it's used for mass spec, is done at typically very low concentrations, 0.05% or less. So we needed an alternative ion pairing reagent that is MS compatible, and formic acid is usually selected for that. Acetic acid less so anymore. It was at one point at least with proteomics applications, but formic acid has pretty much become a standard. However, a problem that we see is, at least with more basic peptides, in the case of again, maybe some polypeptide drugs, or in the case of the digest other than with trypsin, where you can end up with multiple positive charges on the peptide, we have real problems we can see with peak shape, and I'll go into that a little bit more. Now, stepping back a bit, Dave McCauley had published a series of journal articles in which he offered a mechanistic explanation as to why peak shape and peak capacity of basic compounds, including peptides, are so negatively influenced by formic acid as the additive compared to TFA. And here there's this series of these Macaulay papers I referred to, and this was the previous reference as to why TFA, a mechanism explaining why TFA interferes with ionization of peptides in an atmospheric pressure source. So this postulate that Macaulay has is outlined as follows. Basically, is that TFA at 0.1% volume pH is about 2. It's 98% ionized, and so the TFA anion is about 13 millimolar. Formic acid, on the other hand, at a typical 0.1% volume, which again is routinely used, with a pH of the pH at 0.1% is 2.6, the pK is 3.7, so it's only 7% ionized in this case, and the formate anion is approximately 2 millimolar. So there's quite a bit of difference here in the amount of anion that can potentially ion pair with these basic moieties. However, if you titrate formic acid to pH 3.5, you're now 36% ionized. The formate anion is close to 10 millimolar, and what you see is much improved peak shape. This is what David Macaulay again noted with using small molecules, and we are basically taking his suggestions and seeing how it would apply to peptides. So we have this set of standard peptides that differ simply in their basicity, all similar They also differ in their hydrophobicity, but the only really polar moiety here are these lysines. So the basic, this is just a summary of the conditions. Again, this is the columns we use, some various ones. The 0.1% additive, and the same in the final concentration of mobile phase B. Did a constant gradient for these different columns you're looking at. This additive, again, it can be TFA, or in the case of formic acid, unadjusted, pH 2.6, or else we're adjusting it with ammonium hydroxide to pH 3.5. And this is, again, a typical chromatogram you'd see with these 4 peptides, increasing hydrophobicity as well as basicity, with a charge of 1, 2, 3, and 4. If under those, using formic acid now with for mass spec detection, what you see here is as you increase the basicity, the peak shape really declines. And here's an example then to show this general phenomenon. This was simply the first column we were using. This is a relatively new column that we have. It's a fused core or core shell type particle, 160 angstrom, so it's ideally suited for peptide chromatography. Here you see what this chromatogram looks at, like with 0.1% formic acid. If you titrate at 3.5, peak shape improves significantly. We don't yet know what the reason is for this much reduced response of the second peptide compared to the other 3. But here you see, again, verifying this improvement in peak shape with this alternate mobile phase. And looking at just 2 other columns for comparison, this is another one, happens to be a wider pore, 3.5 micron. You see the same sort of pattern. Likewise with another column that's used quite a bit for this application. Same thing. So it's the same general pattern, but we're seeing we would see differences in the extent of the problem. What we see is that there's this general phenomenon. Even though you may have differences between the columns, to the extent to which they show this, it is a generalization. But we want to understand a little bit more about why. And one of them is this possibility, as Dave McCauley postulates, is the availability of formate as a counterion to ion pair with these basic moieties to reduce charge-charge repulsion between adsorbed or non-adsorbed analyte. Another possibility is the mitigation of ionic interactions with silanols. In the case of the pH 3.5, not only do you have the formate anion concentration boosted 5-fold, but counterion ammonium is also introduced. So in order to differentiate between these two, we wanted to do an additional experiment. Again, as I just stated, in titrating formic acid to pH 3.5 with ammonium hydroxide, the final concentration of ammonium cation is about 8 millimolar. So the idea then is simply prepare an 8 millimolar ammonium formate solution, titrate it down to pH 2.6, and what do we see as the result? So here again, this is what I showed you just previously in this with a 0.1% formic acid. We have about 2 millimolar formate anion. If we titrate it to pH 3.5, we now have about a 9 millimolar formate anion, but we have an 8 millimolar ammonium cation. So if we then do 8 millimolar ammonium formate and titrate it down to pH 2.6, we now get results that are very comparable to the case where we have formic acid and titrate it up with ammonium hydroxide. So what we conclude from this is that it's a recommendation from all these studies we've done with a variety of columns. I just showed you a few of them here. Is that where 0.1% formic acid gives issues of peak shape, employing a pH 3.5 buffer is a good alternate option, and that can be done in one of 2 ways, as I've shown. But as I indicated, there are results in terms of the extent of the problem with different columns. So one thing we haven't done yet, but we would like to do, would be to do a bit of an investigation into absorption isotherms of these basic peptides with the different columns to see if there are different classes or types of silanols on the surface. And again, if you're doing typical tryptic digest, you probably will find that this isn't necessary to use this alternate mobile phase. It's the case of peptide samples that happen to be particularly more basic. Again, this is summarizing what I have indicated. And so it looks like from these studies that in our case, it's the ammonium cation, in fact, that is what's responsible for the improved peak shape. One other thing to keep in mind in doing any peptide work is that often surface deactivation is not an uncommon problem, even with modern silica-based particles, as we've shown here and we work with. So consider column pretreatment, and this is it's often we find it's very effective. So I'm going to jump to the second topic then here, and some size exclusion chromatography done on a new line of Discovery Bio GFC, gel filtration, size exclusion. This is available in 3 or 5 micron particles, pore size from 100 angstrom up to 2,000 angstrom. These very large pore sizes are really more useful for actually vaccine and virus development. We don't do a lot of that, but we have other customers who are using it for that. By far, most of the applications you see with proteins are like between 150 to 400 angstrom is by far the most popular, and you'll see that in a little bit. And it contains a hydrophilic, proprietary hydrophilic bonding to this type B silica, modern silica. So what I'm going to show you here, for example, with these separation with this new product line, is just looking at a IDES protease fragments of IgG. It cleaves it into 2 fragments, FAB prime 2, which is about 100 angstrom, and a singly cleaved FC, which is about 25,000. This protease is available from Sigma as well, immobilized on agarose bead and microspin columns that facilitates processing of the sample and fractionation. So again, this is just a diagram of what we're doing. Again, a typical diagram of a IgG with the protease that cleaves again in this hinge region of the antibody to make this Fab2 and this singly clipped FC, and then doing some type of disulfide reduction, you can get these 3 separate fragments. Now in here, this is again, it's just a cartoon, but in fact these are all fairly similarly sized, 23 to 25,000. So these really can't be resolved by size exclusion, but monitoring cleavage and even possibly for purification for downstream characterization, size exclusion is feasible for that. So what we did is I took a purified monoclonal antibody obtained from a colleague at Sigma in St. Louis, did proteolysis with this product, as I indicated earlier, that is this immobilized IDES protease, and then in some cases did sulfhydryl reduction with DTT, and recently looking at some other reductants. But in any case, various fractions then are chromatographed on a 30 by 4.6 millimeter ID column, all 3 micron. Mobile phase. This is all very typical for size exclusion chromatography of proteins. So what you see here on this 150 angstrom pore size is the intact IgG. You can see a little bit of the aggregate here. If you do a partial digestion, you can see on these 2 different, the 150 angstrom particle and the 300 angstrom particle, there are some differences in retention and resolution of this aggregate from these various fragments. Certainly this larger pore particle is better at resolving these higher molecular weights, and the smaller pore is slightly better at resolving these other fragments. This then is now complete digestion, where you simply have these 2 fragments. This is the FAB, and this is the singly clipped FC, sorry, the FAB2. These are now for these purified fractions, which is facilitated again by this immobilized protease and a second affinity column of some type that is used for specifically retaining this FC fragment. So that's what this unretained and retained refers to, this second step affinity matrix. And so you can see here these are nicely identified, and you can see it does this does a nice job, this capture select affinity media selectively for the FC. This bit of contamination really could be eliminated largely simply by additional washings. Then we're doing partial reduction again of this Fab2, again this gets reduced. There's some of it that seems to be left over, but the FD and the light chain fragments co-elute. They're both right, very close to 25,000. And again, if you do the mixture of the two cleaved fragments and reduce them, of course, as I said, those three can't be resolved. But there you see all of them. So Discovery Bio GFC is a high-performance size exclusion media that is useful for resolving biological macromolecules. And it's I've demonstrated to you some nice separation of antibody fragments that can be done by this method. So I'm going to shift now to this third topic, going from large molecules into small molecules. This term bioanalytical has changed over the last 20 years, I'd say, when it used to traditionally mean components related to large biological macromolecules, DNA, protein, and constituent amino acids even. But now it's starting to refer to really analysis of any components from biological fluids. So we're seeing now, again, this term that's used for analysis of other small molecules in biological fluids, as I say. So, I see. I'm not sure what that is. But conventional sample prep is not, yeah, there's a table there that's, I'm sorry about that is missing. Conventional sample prep methods are not effective in reducing phospholipids. Phospholipids cause problems with matrix effects of ionization suppression in mass spec sources. It can alter chromatography and gives poor reproducibility of results. This is what you're seeing here, simply a chromatogram. This is an MRM. I can't tell you for sure which MRM it is, but this is specific for phospholipids, for looking at the polar head group of phospholipids. And you can see you get a variety of components that are coming off in a gradient, a reverse phase gradient, across a variety of retention window times there. So, as I was saying, then conventional sample prep, here's this table. There's various methods: liquid-liquid extraction and modifications thereof, solid phase extraction, protein precipitation. In all cases, there is no really good removal of phospholipids. So, a objective here was coming up with a sample prep method specifically for removal of phospholipids to improve mass spec detection and reproducibility with LC-MS methods. So what we have is this hybrid SPE, which is, again, specific for phospholipid removal. It's a proprietary zirconia-coated silica. Zirconia is a Lewis acid. Phosphate is a strong Lewis base. By manipulating the solvent conditions, we can fairly selectively solubilize the phospholipids, and then we can retain them on this zirconia-modified silica surface. This is showing you a scale of Lewis base strength. And as I say, phosphate is really quite strong. The only real way to displace phosphate is with hydroxide. But this is useful here in the fact that particularly formate, acetate, and citrate, these carboxylates, are less strong Lewis bases, and we can use them in some modified protocols. Really, the protocols for about 80-90% of the cases for sample prep of drugs out of plasma can be followed by one simple method. We have modifications, again, for cases that are specifically basic or chelators in some other protocols with formate or ammonium formate, I should say. So the idea here is that what you can do within this, whether you're talking about free cartridges or in a 96-well plate, we have a one-step procedure that involves bringing the sample to about 75% acetonitrile, acidifying it with formic acid. You get precipitation above the matrix. The sample can get pulled through with the phospholipids retained. And you see that here shown diagrammatically. Precipitate the proteins in the 75% acetonitrile, 1% formic acid, do the mixing, apply the vacuum. The precipitated proteins are retained by a filter here, and the phospholipids are retained in the matrix. and then your eluate is ready for analysis. So showing you again, this is what this looks like of these phospholipids before removal and after removal. With this baseline really blown up, you note the very clean baseline compared to the case where simply protein precipitation has been done. So I'm going to just show you one example here with propranolol and a 4-hydroxy metabolite from rat plasma. This is what the chromatography on a Synthesis Express F5. Again, this is a fused core particle with a perfluorinated phenyl ligand on it. Mobile phase is 90% acetonitrile, and this is done with by mass spec detection. Here you can see the hydroxy metabolite and the propranolol. So comparing standard protein precipitation, again, this is the same sort of pre-treatment as with the case of this hybrid SPE. The only difference is that the phospholipids aren't removed by the hybrid SPE cartridge. So this is the response if you simply do protein precipitation, where you see these peak heights here, and you see massive amounts of phospholipids that are retained by the column as well. If you do the hybrid SPE sample processing, you have a 4-fold increase in sensitivity of propranolol, and you look at your phospholipid profile, and there's basically nothing. This hybrid SPE is very effective in removing phospholipids. And here again, you see this approximately 4-fold improvement in the propranolol compared to standard protein precipitation. So the hybrid SPE is effective in a one-step procedure in removing phospholipids. Proteins are precipitated in the wells of the plate, filtered. The phospholipids are retained by the matrix. And you get a sample that is cleaned up very effectively from biological matrices. And one of the real advantage that we haven't mentioned here at all is really prolonged column life. We've done these sorts of studies looking at back pressure and buildup of phospholipids, and it's instead of a typical case where you often are running gradients to clean up columns, not only is that gradient removal actually over time is ineffective. You might think it looks effective if you're just doing it once, but over time phospholipids are in fact accumulating. But if you do this pre-treatment with applying this hybrid SPE, we see that, and as I showed you here, the amount of phospholipids on the column is drastically reduced, and you don't need to do this sort of gradient cleanup nearly as often. So what I've shown you here today is some recent methodologies that have come out of our bioanalytical R&D group at Supelco in the last few years. We looked at an alternate LCMS mobile phase for peptides in cases where peak shape is less than satisfactory. I showed you some size exclusion on a new product line with antibody fragments. So this is an effective way for assessing the digestion of antibodies, as well as possibly some small-scale purification, especially maybe perhaps we have some folks that are doing this in a 2D arrangement with reverse phase chromatography. And then we looked at effective removal of phospholipids from biological plasma matrix as an effective way to reduce matrix interference for LCMS in the MS source. So with that, I'm done. Thank you.